Good day, viewers. Welcome to the Physics Mind. Today we will be looking at dimensional analysis. Okay, first of all, what is dimension of a physical quantity? The dimension of a physical quantity is the representation of that quantity in terms of the fundamental quantities. That is to tell you that every quantity must have its root traced back to the what? The fundamental quantities. So that is what dimension of the quantities are. When we talk about analysis, that is dimensional analysis is the representation or is a method or technique of representing or showing the relationship between what? Measured quantities. So any two or three quantities that are related together, we can actually use dimensional analysis to do what? To show the actual relationship that exists between them. All right, so for now, we are going to take some simple quantities and we are going to look at how we can obtain their dimension. All right, the first three fundamental quantities we are going to start with are the mass, the length, and the time. So we have mass, and the dimension of mass is a fundamental quantity. So the dimension of mass is capital M. That is the dimension of mass. And the next quantity is what? Length. The dimension of length is what? L. Remember that length is also a fundamental quantity. The next quantity is time. The dimension of time is capital T. All right, now the next quantity we will be looking at is area. Now, area is not a fundamental quantity. Area is a derived quantity. So we have area, and area we know is length times breadth. And the dimension of length we know is what? L, times the dimension of breadth is also what? L. So L times L, that will give us what? L squared. That is the dimension of area. So the next quantity is volume. And volume we know is what? Length times breadth times height. And multiplying their dimensions, that will give us L times breadth is also L times height is also L. So we multiply that, we have what? L cubed. That is the dimension of volume. Now, the next quantity is density. Let's look at density. Now, density we know is defined as mass per unit volume of the surface. So, density is mass over volume. And dimension of mass we know is m. And the dimension of volume we already know is what? Is L cubed. So that gives us the dimension of density. So from indices, I can write it as ml per minus 3. So that is the dimension of density. Now the next quantity we will be looking at is velocity. And velocity is defined as the rate of change of displacement with time. So is displacement over time. And the dimension of displacement is also what? Length. Dimension of displacement is length. So it's L over time is what? T. So from indices, I can write it as LT minus 1. So that is the dimension of velocity. Now, the next quantity is acceleration. And acceleration we know is the what? The rate of change of velocity with time. So it's defined as velocity over time. So let's substitute their dimension. Velocity we know is equal to LT minus 1. We've derived that already. And time we know is what? Is T. And from indices, this is the same thing as what? LT minus 1. When this t goes up, that becomes times t raised to the power of what? Minus 1. So giving us LT minus 2. So that gives us the what? The dimension of the acceleration. Now the next quantity we will be looking at is the that is number 9. Let us look at the dimension of force. And force we know is the product of mass times acceleration. So force is equals mass times acceleration. So that will give a dimension of mass is m times the dimension of acceleration we know is LT minus 2. So that gives us mLT per minus 2. That is the dimension of force. Now the next quantity we will be looking at is work done. Work done. So let's look at the dimension of work or energy. Now, both work and energy have the same dimension. Remember, they also have the same SI unit, so they also have the same dimension. And work we know is defined as the product of force times distance. Force times distance. And the dimension of force we know is what? mLT per minus 2 times distance. Distance also have dimension as length, which is what? Capital L. So that gives us, or multiply that from indices, we have m, L times L, that will give us L squared, then T per minus 2. So that is the dimension of work and also the dimension of energy. Now, the next quantity we will be looking at is power. Now, let's look at power. And the power we know is defined as the time rate of doing work or the rate of work done with respect to time. So, power is work done over time. So, substitute their dimension. Work done we already know is ml squared t per minus 2 over time, which is what? T. And that will give us ml squared t per minus 2. Remember, when this t goes up, it becomes, or from indices, we can take it as minus 2 minus 1. Remember, the power of t here is what? Is 1. So I can take it as ml squared, then t minus 2 minus 1. Remember, from indices. So that will give us ml squared t per minus 2 minus 1. That will give us minus 3. So that gives us the what? The dimension of power. And lastly, we will be looking at the dimension of momentum. The dimension of momentum. Momentum we know is defined as the product of its mass and its velocity. So momentum is defined as mass times velocity. So that gives us dimension of mass we know is capital M times dimension of momentum, dimension of velocity is LT per minus 1. So we'll multiply that. That will give us MLT per minus 1. So this gives us the dimension of momentum. So we've come to the end of today's class. Please make sure you subscribe for the next video for the continuation of the topic. Bye.